Hello everyone. In this video we are going to see the introduction and representation of graph data structure. These are the contents of this video: a definition, basic terminology of graph data structure, and also we will see the adjacency list and adjacency matrix representation of graph data structure. Right, okay. Just come to the definition of graph. See, so graph is, already graph is a non-linear data structure, right? And defined as, you can say, the set of vertices and set of edges, right? And set of vertices must be finite and non-empty set, okay? And where this is the vertex, right? This is vertex, and this is the edge. Edge is the set of pair of vertices representing the edge. This is edge, right? Okay. So simple. In this picture, in this diagram, you can say this A, B, C, D, E, F. A, B, C, D, E, F are the vertex, and AB, this AB, AB is a edge. Similarly, AC is also edge. So there are different edges are there and different set of vertices are there, right? Okay. Now, yes, these are the some application of graph data structure. This graph data structure is one of the very powerful data structure in terms of implementation of different software and applications. Like, these are the some applications where graph data structure is applied. For example, so Google Map. In Google Map, all the intersections, suppose in Google Map there are lots of cities are there, and these cities are considered as a node or item. Node and the road represents the links, right? So these are the nodes, these are the city, you can say, and these are the roads. So you can say that this map application is also one of the example of graph data structure. Similarly, in web content, website, suppose different pages are there, and different pages, these pages are considered as an item or nodes, and links are considered as an edge or connection. Suppose you are going to, in website, suppose you are going to click on particular hyperlink, a particular URL, you say particular link, then another page will be open, right? So this link are what? Edge, and these pages are what? Nodes, right? Suppose in circuit, digital circuit, you can say, devices are considered as a nodes and wire are edges, right? Okay. In scheduling, suppose scheduling, and suppose I'm going to for example, suppose I'm going to create a timetable of the class. So different subjects in timetable, different subjects are considered as a job. Job as means node, right? And constraint, there are some constraint at the time of designing the timetable or scheduling, right? Suppose in timetable, particular lab will be after post lunch, you can say, right? So there are some constraint are there. So you can say constraint are what? Linking. Constraint are connection, edge, okay? And another one is in commerce side. Commerce side, customer are the nodes and transactions are the connections. In matching, students are the nodes and applications are the connection. Very important. And in computer networks, different sites are considered as a node and connection are what? Edge. And very important in terms of software. In software, method are considered as a node, and different calling the methods, function calling is considered as a edge. For example, suppose I'm taking the simple application like factorial program. In factorial program, suppose you are going to write a factorial program as a recursive, then factorial is calling factorial for 5. So this is method. This method is going to call what? 5, going to call the factor 5. So this calling is considered as an edge. In simple application I am telling you, but in software also, software is this collection of method, you can say, integrated methods. So the method is also a node, and call is what? Different calling is connections. Okay. In social networking, very interesting. Graph is an example of social networking sites also. A person is considered as a what? Node, and friendship considered as a edge. Like social networking sites. Some examples are uh, Facebook, and Twitter, right, and Instagram. One more thing I would like to share here. Facebook is an example of undirected graph. Undirected graph, right? And Twitter and Instagram is an example of directed graph. Why? Suppose a person who is friend of yours in Facebook, then definitely that person is also friends of yours, and you are also a friend of that person. Okay, and got my point. And in Twitter and Instagram, a person who is following you does not means you are also following him. Got my point? Or a person who is following you, a person who is following that person does not means that person also following you. This is not a undirected graph. This is the example of directed graph, right? And Instagram also similar like Twitter, right? So remember this one. Twitter and Instagram is example of directed graph, and Facebook is the example of undirected graph. So these are the some applications of graph data structure. Now come to the basic terminology of graph. So first one, adjacent node, vertex. Okay, you can say node, adjacent node, yeah, adjacent vertexes. Simple. Vertex V1 is said to be adjacent to vertex V2 if there is an edge between the V1 and V2. These are the, suppose let me tell you, vertex ACD. What ACD are adjacent of this vertex B, because ACD are connected with this vertex. This connection, this connection, this connection. It means ACD is the adjacent of this vertex T, right? Similarly, E and F is the adjacent of D vertex, right? That's very easy. Okay. Okay. Now, path. What is simple? Simple path is the sequence of vertices between the two vertices. For example, suppose CABD is the path from C to D. Suppose I am going to tell you from C to D. From C to D, what is the path? CABD is the path, one path. Okay. Remember, there may be more than one path to traverse from one vertex to another vertex. In graph especially, right? There may be more than one path from one vertex to another vertex. But in case of tree data structure, only one, there must be exactly one path from one vertex to another vertex in tree data structure. But in graph, there may be more than one path. For example, suppose I am going to from C to D. There are two paths, CABD and CBD also. This is C and this is CBD. This is another path. Okay, remember this one. Another point is this. Suppose this is the path. A path is said to be closed if the end points of the path are same. This is suppose A, B, C, A. This is also a path, but this is the closed path because the starting point, the end path. This is the end point, and the both end points are same. A and A are same. This is the closed path. And simple path CABD is the simple path. In the path is said to be simple if all the vertices sequence are distinct. They should not be same. ABC, CABD is the simple path. But CABC is the closed path. Okay. Now, next, what is cycle? Cycle is the closed simple path, right? Cycle is the closed simple path with length 2 or more length. Length means what? The length of path is suppose C to B. C to B, there is the one path length. This is one, and another one 1 to 2 path length, right? Okay. Remember this. The CABC are the cycle. CABC is the one of the cycle, and here is also cycle. DFE DFED is also a cycle, right? Simple. Okay. Undirected graph, there is no specific direction associated with edge. See, A to B or B to A. You can say A to B or B to A. Same thing. This is not an ordered pair, a simple pair. A to B or B to A. Okay. So in directed graph, an edge is represented by the unordered pair. Definitely unordered pair because there is no direction. Right? There is no association. Simple. A to B or B to A. Okay. See, so this is undirected graph. Next is directed graph. Okay. In a directed graph, all the edges are directed. Simple. This is the directed. A to B, but B is not A. A to B. This is ordered pair. A to B, but not B to A. Okay. In the directed graph, an edge is represented by the ordered pair Vx A or A comma B. Then edge is said to be directed from A to B, where A is this starting vertex and B is what? End vertex. Simple. So this is a very easy definition. Directed graph and undirected graph. You should remember this point, these points. Okay. Connected graph. What is? A graph is said to be connected if there is a path between every pair of vertices. Definitely. A to B, A to C, there is the path. A to B, there is the path. A to C, there is the path. A to D, there is the path. From A to D, B to D, C to D, there is a path. Okay. But if there is a path between every pair of vertices. Suppose I am taking this another vertex like this one, X. So this is not a connected graph because there is no path from B to X. There is no path from D to X. So there must not be any isolated vertex. This is isolated vertex. Okay. So isolated vertex, there is no connection between any two vertices. Simple. Okay. So this is not a connected graph. But if I'm removing this vertex, then this is the connected graph. Okay. Now, weighted graph. Every edge in the graph is assigned some data. Okay. Or this data can be represented in terms of different scenario. Suppose you can consider as a distance between B and C is 20 unit, right? And or you can say the profit between the B to C is 20. You can consider the 20 data, this data as different scenario, right? Okay. Now come to the graph representation. There are basically two types of representation: adjacency matrix and adjacency list representation. The first I'm going to discuss adjacency matrix. So simple. And this is a matrix, adjacency matrix. Actually, the reason is what? Actually, this graph is a non-linear data structure, and this is also a logical data. This is also a logical data structure, and this logical data structure will not be directly mapped in computer memory. So that's why we are going to convert this logical data structure with the help of physical data structure, that is array, two-dimensional array, that is matrix. Okay, so simple. So this is two-dimensional array, that is matrix. Simple. In matrix Mij, adjacency matrix representation of an unordered graph G will be 1. An entry in this matrix will be 1 if there exists an edge between Vi to Vj. Suppose I am going to take the example A to B. A to B, where is A to B? A to B is an edge. It means we are going to put here 1. Right? A to C, this is A to C. A to C, there is no direct path, no direct path between A to C. So I am going to consider here 0. Okay, just put 1 in this matrix if there exists an edge between the Vi and Vj are simple, between the two vertex. That's very easy. Adjacency matrix, this is the unordered, for this unordered graph. Okay, so now I'm going to take the 3 graphs: undirected adjacency matrix for undirected graph, adjacency matrix for directed graph, and adjacency matrix for weighted graph. That's very easy. Okay, this is one of the structure of adjacency matrix. at the time of implementation. So these are the three data members: integer vertex, edges, and adjacency matrix. Double pointer is there. You know already, matrix is the double pointer, right? So that's why I'm going to use double pointer here. Okay. Now come to the directed graph. Adjacency matrix in directed graph. Very easy also. Now in directed graph, entry in this matrix, the entry will be 1 if and only if there is the S directed from Vi to Vj. Suppose A to B, A to B, A to B is there, this is 1. So just I am going to keep this 1 here in this matrix. But not B to A. B to A. In this case, in undirected graph, see the B to A is 1, A to B is 1, right? But in case of directed graph, A to B is only 1, B to A is not 1. This is ordered pair, right? Okay, that's very easy also. And now adjacency matrix in weighted directed graph. Simple, right? Instead of filling the entry by 1, the non-zero entry of the adjacency matrix are represented by the weight of the respective edge. Right? Suppose I'm going to A to B is 1, right? But now I'm going to put here weight of this edge. Just I'm going to put here 4. Simple, right? So this is the weighted adjacency matrix, you can say, for this weighted directed graph. Okay, let's see the adjacency list for undirected graph, and this representation is also called a no directory representation. This is a directory. See, in this graph, a vertex A is connected with vertex B and D. That's why I'm going to link with B to D. This is B, this is to D from A. Linked representation, right? And from B, this node is connected with ADC. That's why I'm here using ADC, right? And this order may be any ADC, DAC, yeah, CAD, any order you can consider. And this is a null pointer, is this, right? And now C, what about C? C is connected with B and E. So that's why C is connected with B and E. Okay, and suppose this is the address of 1000, 2000, so this 2000 will be linked with this node, right? Now come to this with D. D is connected with ABE, so that's why ABE is linked with D node. Okay, and E is connected with DC, so E is connected with DC. Simple. This is the adjacency list of this undirected graph, and this is the structured node of this adjacency list. Vertex, edge, and pointer adjacency. This self-referential, right? Okay. Now let's see adjacency list for directed graph and weighted directed graph. So, in case of directed graph, simple. Ordered pair is there. A is connected with only B, not D. This is not a directed. This is not a direction. So A is connected with B, so that's why A is connected with B, and this is the null pointer. Similarly for B, B is connected with C and D. B is connected with C and D, right? And for the C, C is connected with E only, right? And D, vertex D is connected with A only. This is A, right? And E is connected with D only. So this is the linked list. This is linked representation of what? Directed graph. The simple difference, there is a difference, slight difference between the directed and undirected, right? Okay. Now, in case of weighted directed graph, adjacency list, just I am going to put the weight of that edge. Okay. Just in this case, in node, there are 3 partitions. First is the information part, another one is the weight of that edge, and this is the next part. Okay, right? So vertex from vertex A, there are 2. How many edges are connected? Only one edge are connected. One vertex is connected. That is B. So A to B is connected, and what is the edge? This is 5 edges, and this is null pointer. What about B? B is connected with D and C. So this is C and D with edge, with weight 2 and 8. Now you can consider here is the same. This adjacency list and this adjacency list is same, but one data member is added, right? That is weight. This is the 5 weight. This is the 2 weight, right? And for this D is 8 weight. Otherwise, this adjacency list are same. Okay, but in case of unweighted directed graph, we just consider uh, weight of a particular edge for this one extra part of the node, right? So these are the representation of graph. Okay, so thank you for watching.